Today we will dive into the world of semiconductors and journey through the incredible creation that is the Gunn Diode. From its inception and its inner workings and numerous applications, this small device has a big story. So the content of this video will be to understand the history of Gunn Diode, and then we'll proceed to the structure, working principle, and the last one, the applications of the Gunn Diode. Gunn Diode is named after Dr. J.B. Gunn, a physicist at IBM. While studying the properties of gallium arsenide, he discovered that when a sufficient large voltage was applied, there was periodic fluctuations of current passing through the n-type gallium arsenides that caused high oscillation frequencies. This phenomenon was later known as Gunn effect, which can be explained by Rayleigh-Watkins-Hillsum RWH theory. Now let's look at the structure of a Gunn diode. At its core, it is a piece of n-type gallium arsenide, and the diode is constructed of two highly n-doped areas and a thin region between them with a low concentration of dopants, which is what we call as active region. And then the two highly doped regions provide a better conductivity to the device. And also the Gunn diode also has two ohmic contacts at either end, which are used to connect it to an external circuits. And gallium arsenide has extra energy band, which is a unique characteristic than other semiconductor, which is what we call as upper valley and lower valley levels. To understand the working principle of a Gunn diode, we need first to understand on how the Gunn diode can create negative differential region of Gunn diode, where the current will decrease as the voltage increases. So this NDR region will serve as a basis for oscillation to work. In order for the Gunn diode to work, first we need to apply voltage and electric field to the Gunn diode. So when we apply electric field to the Gunn diode, it will separate into three regions, which is, as you can see, this one at the graph below. So this is the first region, this is the second region, the negative differential region, and this is the ultimate bulk region. Okay, it's the third region. So for the first region, when they apply electric field increasing, but the value is less than the threshold voltage but more than the EG, forbidden gap voltage, electrons will be excited to the forbidden band and to the conduction band, which is the lower valley, and this will cause the increase in drift velocity, resulting in positive mobility of electron. Hence, this will increase the current and also resulting in positive resistance. But when the electric field increases above a threshold voltage, the electrons gain more than the 0.36 electron-volt energy that separates between the upper valley and the lower valley, and as a result, electrons can be scattered into the upper valley, where the density of states and electron effective mass is much larger. This transition reduces the average drift velocity, and as a result, reduce also the electron mobility. This will result in decrease in current and as the voltage increase. This is what we call as negative differential resistance region. When the electric field is increased above the valley value, drift velocity will increase, and this will result in positive mobility and also will result in the increment of the current and positive resistance. So NDR will help establish the condition that's suitable for the initial oscillation of the Gunn diode. As you can see, the electrons moving from the valence band to the forbidden gap and also to the lower valley and to the upper valley. So how the electrons move. Okay. So from the graph below, this is the variation of drift velocity with electric field, where at first, below the threshold value, when we apply electric field to the Gunn diode, so the current will be linear, increase, and then out of sudden in negative differential region, the current will decrease, and after the electric field EV value, it will then increase back. After we understand the negative differential resistance region, so let's understand on how the domain of Gunn diode form. So first, when the electric field surpasses the threshold value, a high field domain with a high electric field intensity form in the NDR region. So this domain will move across the diode and propagates towards the anode, causing the electron in its path to shift to the upper value. The domain's velocity, its movement, is slightly higher than the drift velocity of the electrons. So the domain movement then will modulate the current as the domain passes through the regions of different dopings and cross-sectional area of the Gunn diode. As you can see before on the previous slide, you can see that the Gunn diode is consists of a few layers that is in different doping concentration, which is the active region. So this action of movement through different doping concentration and cross-sectional area will generate initial oscillation. So once there is initial oscillation, we need to perturbate this oscillation with an input and external input signal. This will trigger the onset of oscillations. Once the oscillation are initiated, a portion of the output signal is fed back into the system through a positive feedback loop to make sure to maintain the self-sustained oscillation of the Gunn diode. The NDR will enables the initial generation of oscillations, and the feedback loop maintains and reinforces back the oscillation so that it will reoccur and being a self-sustained oscillation. So to make it simple, so the Gunn diode will first create a negative differential resistance region, which is the region that surpasses the threshold value of the electric field, and then this region will then create a domain, and this domain will propagate throughout the diode. So since the Gunn diode only consists of N-type gallium arsenide with different doping concentration, and different conductivity, this will generate initial oscillation. So because of this initial oscillation, we can then perturbate it with external input signal so that it triggers the onset of oscillation. So once the oscillations are initiated, a portion of the output signal is then fed back into the system through a positive feedback loop, so that it can maintain and establish a self-sustained oscillation. So basically, the NDR is the key point where it will enables the initial generation of oscillations, and the feedback loop, which is also the key, will maintain and reinforce the oscillation. The Gunn diode finds wide application in high-frequency electronics. Its unique properties make it ideal for microwave oscillators used in radar speed guns, satellite communication system, and even electronic warfare system. Additionally, its ability to generate high-frequency oscillations makes it a critical component in many signal generations. So, for example, the signal generators will be used in telecommunications and also security system. For example, wireless network and satellite communication. In security system, you will then be applied in motion detectors to detect motion, intrusion alarms, and also the electronic warfare system. Do you know that the Gunn diode is one of the semiconductors that can generate the highest output signal? So this output signal can be applied in electronic warfare system to disrupt the enemy's electronic system. This will then disrupt the enemies in many ways. For example, will disrupt their communication and also will disrupt their electronics tools such as sensors that they use in wars, for example. So the Gunn diode may be small, but its impact is large. It's a fascinating example of how deep understanding of material science can lead to powerful technology. So the next time you see a radar gun or use of a satellite communication device, remember the humble Gunn diode. So that's all for this video. So let's meet you guys next time.